The universe is whispering to us across billions of years. These faint murmurs are stochastic gravitational waves, random ripples in spacetime from the Big Bang and countless cosmic collisions. By the end of this, you will understand the incredible methods scientists use to hear the universe's oldest song. We will uncover how we hunt for these echoes from nowhere and what their discovery could reveal about the very first moments of existence. How do you listen to a whisper from the dawn of time? Think of the universe as a vast, silent ocean. For centuries, we have been watching the waves on its surface, the light from stars and galaxies. But beneath that shimmering surface, in the deep, dark depths, there is another kind of motion entirely. This is the realm of spacetime itself, a cosmic fabric that can be stretched and squeezed. Albert Einstein's brilliant theory of general relativity painted this picture over 100 years ago. He proposed that objects with mass do not simply pull on each other mysteriously. Instead, they warp the very fabric of reality around them. A star is like a heavy ball placed on a stretched rubber sheet, creating a deep well. A planet orbits not because it is being pulled, but because it is following the curved path of that well. This is gravity. Now, imagine giving that heavy ball a sudden, violent shake. The depression in the sheet would not just change shape, it would send out ripples. These are gravitational waves, not waves of water or sound, but waves of geometry itself. They are rhythmic, traveling distortions in the distance between any 2 points. When one passes, the space you occupy literally stretches and compresses in a rhythmic dance. The most powerful events in the cosmos create these ripples. Colliding black holes, merging neutron stars, even the violent birth of the universe. But a single event creates only a fleeting whisper. The signal scientists are desperately hunting is the combined effect of them all, a chaotic chorus of every ripple that has ever traveled through the cosmos. This is the stochastic background, a random, persistent hum of spacetime vibrations. It is the fossil record of the universe's entire history of violence, a soundtrack written not in sound or light, but in the subtle, ever-present trembling of reality. This background hum is fundamentally different from the signals we have already captured. When LIGO and Virgo detected their first gravitational waves, they heard clear, distinct chirps. Each one was a precise cosmic event, a fleeting scream from 2 black holes or neutron stars spiraling into each other. The stochastic background is not a scream or a chirp. It is the static. It is that low, persistent hiss you might hear between radio stations, a random noise that seems to contain no information. Yet this cosmic static is not meaningless. It is the sound of everything else, the combined murmur of every single gravitational wave event that is too faint or too far away to be heard on its own. The term for this is stochastic, a scientific word that simply means random and unpredictable in its fine details. You cannot know exactly what the next moment of this hum will sound like because it is built from an uncountable number of tiny, overlapping whispers. What creates this cosmic chorus? The primary contributors are the mergers we already know exist, just on a grander scale. Imagine the combined signal from millions upon millions of binary black hole pairs and neutron star pairs, all merging throughout cosmic history, their individual ripples overlapping into a steady, chaotic rumble. But the sources could be even more exotic. Some theories point to phase transitions in the searing heat of the very early universe, moments when the fabric of reality itself changed state, like water freezing into ice, sending violent tremors across the cosmos. Other possibilities include cosmic strings, hypothetical defects in spacetime, or vast populations of primordial black holes born from the Big Bang itself. All of these potential sources contribute to a single, diffuse signal, a low-frequency vibration that perpetually passes through everything, including you. Detecting it is an exercise in supreme patience and cleverness. It is the ultimate listening challenge. You are not trying to hear one person shouting in a quiet room. You are in the middle of a roaring, crowded stadium, and your goal is to isolate the collective, indistinct murmur of every single conversation happening at once. That collective murmur, however, is the key to a deeper truth. It is a fossil record of the universe's entire violent history, and buried within its random noise could be the faint, distorted echoes of creation itself. To understand why this hum is so precious, we have to travel back to the very beginning of everything. The very first moments of the universe were a cauldron of pure energy, a realm so extreme our current physics struggles to describe it. Within the first sliver of a second after the Big Bang, a pivotal event may have occurred known as cosmic inflation. This was a period of staggeringly fast expansion, where the universe ballooned in size at a rate far exceeding the speed of light. During this violent growth spurt, the tiniest of quantum jitters, the inherent fuzziness of spacetime at the smallest scales, were stretched to immense proportions. Think of the universe as a rapidly inflating balloon. If you draw a tiny, wiggly line on its surface before blowing it up, that small, random wiggle becomes a massive, landscape-defining feature as the balloon expands. In the same way, those microscopic quantum tremors were amplified into vast, undulating ripples in the fabric of spacetime itself. These are the primordial gravitational waves. They are not from colliding black holes, but from the birth pangs of the cosmos, a direct echo of creation's first instant. This makes them the most ancient messengers possible, carrying a pristine signal from a time before the first light even existed. The cosmic microwave background, that famous afterglow of the Big Bang, was emitted hundreds of thousands of years later. But these gravitational waves come from a time so early it is almost incomprehensible. Finding them would be the ultimate confirmation of inflation, a smoking gun from the universe's very first chapter. It would be like uncovering a fossil from the exact moment life began, but for the cosmos itself. This incredible promise, the chance to read a telegram from the instant of creation, is what fuels the relentless push to build machines capable of hearing this faintest of whispers. On September 14, 2015, a whisper finally reached Earth. After traveling for over 1 billion years, a ripple in spacetime, generated by two black holes colliding, was captured by the twin LIGO observatories. The signal was not a random hum, but a precise, rising chirp that ended in a final, silent merger. This single event was the opposite of the stochastic background, a loud, transient scream in the cosmic quiet. Yet its detection was everything. It was the first direct proof that the cosmic fabric really does ripple, just as Einstein predicted a century ago. More than that, it was a stunning demonstration of human ingenuity. The laser interferometers at LIGO measured a distortion in spacetime thousands of times smaller than the nucleus of a single atom. To grasp that scale, imagine measuring the distance to our nearest star, Proxima Centauri, and detecting a change in that distance no wider than a human hair. That is the level of sensitivity required to hear the universe's faintest songs. This monumental success did more than confirm a theory. It flung open an entirely new window on the cosmos. Before this, we studied the universe almost entirely through light, from radio waves to gamma rays. Now we could feel its vibrations. The LIGO chirp validated decades of painstaking engineering and theoretical work. proving that our machines could indeed sense the subtle stretching of space itself. With that foundational confidence, the hunt for fainter, more elusive signals became a tangible pursuit. If we could hear a cosmic shout, then perhaps we could learn to listen for its background murmur. The key to this entire endeavor, the tool that made both the loud chirp and the quiet hum detectable, is a technological marvel of light and precision known as the laser interferometer. This device, the laser interferometer, operates on a principle of profound simplicity and equally profound sensitivity. Think of it as the universe's most attentive listener. At its core are two long, empty tubes, each several kilometers in length, arranged in a perfect L shape. A single, incredibly pure beam of laser light is fired and then split in two, with each half cent racing down one of these colossal arms. At the end of each tunnel, the light bounces off a suspended mirror and races back to the starting point. Under normal, quiet conditions, when no gravitational wave is passing through, the two returning light beams are perfectly matched. They are arranged so that their waves cancel each other out, a phenomenon known as destructive interference. The result at the detector is darkness, a silent confirmation that nothing has changed. But then a ripple in spacetime arrives. It is not a wave that lifts and lowers anything. Instead, it subtly and rhythmically stretches the space along one direction while simultaneously squeezing it in the perpendicular direction. For the interferometer, this means one of its long arms gets infinitesimally longer, while the other gets infinitesimally shorter. The change is almost nothing, a shift in distance far smaller than a single proton. Yet that tiny difference is enough. It changes the travel time for the laser light in one arm relative to the other. Now, when the two light beams return and try to recombine, they are no longer perfectly in step. Their waves no longer cancel out completely. Instead, a flicker of light appears at the detector. That flicker, that tiny defeat of the expected darkness, is the signal. It is the whisper translated into a glimmer of light. The precision required to see this is beyond human intuition. It means measuring a change in length so small it is like measuring the distance to our nearest star, Proxima Centauri, and detecting a variation no wider than a single human hair. This is the bedrock of the entire search, the reason we can even dream of hearing the faint hum of the cosmos. But one listener, no matter how sensitive, is not enough. A flicker of light in one machine could be anything: a small local earthquake, a distant rumble of a truck, or just random noise. To be sure you are hearing the universe and not the planet, you need a chorus of listeners, a global network comparing their notes. A single observatory, no matter how advanced, is a lonely listener prone to deception. A flicker of light in one machine could be a passing truck, a minor earthquake, or just the random noise of its own electronics. To be certain you are hearing the universe and not the planet, you need a chorus of listeners spread across the globe. This is the power of the network, a collaboration between LIGO in the United States, Virgo in Italy, and Kagra in Japan. These facilities work in concert, their data streams combined and compared in real time. The logic behind this is beautifully simple. A genuine gravitational wave, a ripple in the very fabric of reality, will wash over the entire Earth. It will arrive at each detector with a tiny, calculable delay, a difference of mere milliseconds dictated by the exact distance between them. A local rumble in Louisiana will not show up in the Italian countryside. By searching for these correlated signals, for the same subtle pattern of stretching and squeezing appearing in multiple detectors at just the right times, scientists can perform a kind of cosmic subtraction. They can sift the faint, universal hum from the cacophony of local noise. This global partnership effectively stitches these separate instruments together into one colossal, planet-sized ear. Its sensitivity is far greater than any one observatory could ever achieve alone, and its credibility is ironclad. Yet, even this powerful planetary ear strains to hear the deepest notes. The stochastic background is predicted to be strongest at the lowest frequencies, a bass rumble that slips below the optimal hearing range of these ground-based instruments. Their very design, with arms several kilometers long, makes them exquisitely tuned to the higher-pitched chirps of black hole mergers, but the universe's oldest song is a much lower hum. But even a planet-sized ear has its limits. The lowest frequencies of the cosmos, the deep bass notes of the universe's oldest hum, slip right through it. These gravitational waves are not just faint, they are enormous, with wavelengths spanning light years. To catch a wave that big, you need an instrument of corresponding scale, a detector not built by human hands, but forged in the heart of exploding stars. This is where we turn to pulsar timing arrays, a method that uses the galaxy itself as our laboratory. The key players are pulsars, the lighthouses of the cosmos. These are the rapidly spinning, ultra-dense cores of dead stars known as neutron stars. As they spin, they emit a powerful beam of radio waves that sweeps across space like the beacon of a cosmic lighthouse. For some pulsars, this spin is incredibly stable, making them the most precise natural clocks in the universe. Their rhythmic pulses arrive at Earth with a regularity that rivals our best atomic clocks, ticking with unwavering precision for millions of years. Scientists realized that this celestial clockwork could be used to sense the subtlest of cosmic tremors. They began monitoring dozens of these pulsars across the galaxy, carefully logging the arrival time of every single pulse. The concept is breathtakingly elegant. Picture a low-frequency gravitational wave, a vast ripple light years from peak to trough, slowly washing through the galaxy. As it passes through the space between Earth and a distant pulsar, it minutely stretches and then compresses that spacetime. This tiny distortion changes the distance the radio pulses have to travel, not by much, but just enough to make them arrive a little early or a little late. A single shift in one pulsar's timing could be a fluke, but the true signature of a gravitational wave is a specific, correlated pattern of shifts across many different pulsars, all following the rhythm of the passing spacetime ripple. It is a synchronized dance of delays and advances across the entire sky. This is the goal of major projects like NanoGrav in North America and the European Pulsar Timing Array. They have been patiently collecting data for over 15 years, listening to an entire orchestra of cosmic metronomes. Their work has already yielded tantalizing hints, a low rumble in the data that looks exactly like the signal scientists have been chasing. This has electrified the astronomy community, bringing us closer than ever to confirming the existence of the stochastic background. Yet, pulling this faint, correlated signal from decades of data is a monumental challenge in itself, a task that relies on some of the most sophisticated data analysis techniques ever devised. Finding a whisper in a storm requires a kind of statistical magic. The challenge is almost absurd, searching for a random signal buried in noise that is a billion times louder. The primary tool for this impossible task is a mathematical technique called cross-correlation. Think of it as the ultimate cosmic matching game. The logic rests on a beautiful fact: the stochastic gravitational wave background is universal. It is a signal that washes over the entire Earth. This means the same faint, random hum should create a similar, though not perfectly identical, pattern in two widely separated, independent detectors. Imagine two microphones placed miles apart in a roaring stadium. Each one picks up an overwhelming wall of sound: the crowd, the announcers, the stomping feet. But if you could take the recordings from both microphones and compare them with immense care, you might notice that the deepest, most pervasive rumble of the crowd has a subtle, matching rhythm in both recordings. That matching rhythm, found only through this comparison, is the signal you want. For gravitational wave observatories, this means taking the immense, noisy data stream from the LIGO detector in Livingston, Louisiana, and mathematically comparing it point by point with the data from its twin in Hanford, Washington, over 2,000 miles away. A random vibration from a truck in Louisiana will not appear in the Washington data, but a genuine ripple in spacetime will leave its tiny, correlated mark on both. The process itself is a masterpiece of patience. It involves multiplying these massive data sets together and averaging the result over incredibly long observation times, months or even years. The expected correlation is minuscule, a statistical whisper so faint it is utterly invisible in any single moment. But over time, something remarkable happens. The signal, being a real physical phenomenon, builds up consistently in the data. The random noise, by its very nature, tends to cancel itself out. Slowly, imperceptibly, the signal-to-noise ratio grows. This is not a sprint, it is a statistical marathon run over years, demanding immense computational power and unwavering patience to tease out the faint, universal whisper from the cacophony of earthly interference. This sophisticated data sifting is the final, crucial step that transforms raw detector output into a potential discovery. So, what cosmic events are creating this persistent hum that requires such cleverness to find? The cosmic hum is not a single, simple note. It is a layered symphony, a chorus of voices from across time, and our challenge is to learn which instrument is playing which part. Scientists believe this stochastic background is composed of two distinct types of sound. The first is the astrophysical background. Think of this as the combined roar of a cosmic zoo. It is the overlapping chirps from every single binary black hole and neutron star merger that has ever occurred throughout the history of the universe, all too faint and distant to be heard on their own. This is a foreground of relatively recent events, a testament to the violent dances of dead stars over billions of years. The second component is far more ancient and exotic. This is the cosmological background. Its sources are not colliding objects, but the fundamental physics of the universe's birth. It could be the direct echo of cosmic inflation, the tremors from hypothetical defects in spacetime called cosmic strings, or the vibrations from a phase transition in the searing early cosmos, like the crackling of reality itself as it cooled. Disentangling these two components is one of the biggest puzzles in modern physics. Is the hum we detect the murmur of countless black holes, or is it the faint whisper from the Big Bang itself, or a complex mixture of both? The answer lies in the subtle character of the signal itself, the frequency spectrum of the hum, how its strength changes across different pitches, and its statistical properties act like a cosmic fingerprint. The astrophysical background from merging black holes has a predictable shape, while a signal from inflation or cosmic strings would look completely different. This makes the detailed characterization of the signal just as important as its initial detection. Understanding what is creating the hum directly shapes how we build our next generation of listeners. Every whisper from the cosmos must first survive an earthly cacophony. The search for spacetime ripples is not a passive listening exercise, it is a brutal war against noise. Our most sensitive instruments are besieged by a symphony of false signals, each one threatening to drown out the faint universal hum. The ground itself is a constant source of vibration. Seismic noise, generated by everything from distant earthquakes and pounding ocean waves to nearby traffic and even people walking, constantly shakes the foundations of these delicate machines. If you have ever felt a heavy truck rumble past your house, you understand the scale of the problem. Now imagine trying to detect a ripple that stretches space by less than a proton, while the ground beneath you is in perpetual, shivering motion. Then there is the enemy within, the thermal noise, the very atoms that make up the detector's crucial components. Its pristine mirrors and delicate suspension wires are not still. They jiggle and dance randomly, driven by their own heat. At room temperature, this atomic jitter is enough to mimic the subtle push of a passing gravitational wave. Finally, there is the fundamental noise born from light itself. A laser beam is not a perfectly smooth river of energy. It is a stream of individual particles called photons. These photons arrive at the detector in a random, stuttering pattern, like rain on a tin roof. This quantum randomness, known as shot noise, creates an inherent fuzziness in the measurement. Each of these noise sources rules a different part of the frequency spectrum, creating what scientists call a noise curve. It is a map of the battlefield, showing exactly where the static is loudest and where a true signal might finally poke through. The entire engineering effort is focused on pushing this noise curve down, creating a deeper and deeper silence. This involves suspending mirrors on intricate systems of pendulums and filters to block seismic shakes, cooling components to cryogenic temperatures near absolute zero to quiet atomic vibrations, and using immensely powerful lasers to smooth out the photon rain. This relentless, painstaking pursuit of quiet is what slowly, agonizingly lowers the threshold of hearing. It is a battle fought for every fractional gain in sensitivity, a war against the universe's background chatter to hear its oldest song. To truly escape this noisy planet, we must build a listener in the one place guaranteed to be silent, the vacuum of space itself. The ultimate escape from our noisy planet is already on the drawing board, a mission that will carry our listening post into the pristine quiet of space. The Laser Interferometer Space Antenna, or LISA, is a gravitational wave observatory designed not for the ground but for the solar system. Its design is a masterpiece of cosmic scale. Picture 3 identical spacecraft, flying in a perfect triangular formation with each side spanning 2.5 million kilometers. That is a distance more than 6 times the span from the Earth to the Moon. This colossal triangle will orbit the Sun, trailing behind our planet, and its 3 points will constantly fire laser beams at one another. They form a single, gigantic interferometer, but one freed from all the earthly troubles that plague its planetary cousins. There is no seismic rumble here, no passing truck, no atmospheric distortion, only the pure, silent vacuum of space. This immense scale allows LISA to tune into the universe's deepest frequencies, gravitational waves with periods ranging from hours down to seconds. These are the waves that ground-based detectors are fundamentally deaf to, the long, rolling swells of the cosmic ocean. This is precisely the band where the most exciting sources are predicted to sing. Primary target is the choir of monstrous black hole binaries. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, weighing millions or even billions of times more than our Sun. When galaxies collide, these behemoths eventually find each other and begin a slow, spiraling dance that can last for eons. Their orbital motion generates gravitational waves of immense power at these low frequencies, and the combined roar of every such pair in the universe is thought to be a dominant part of the stochastic hum. LISA will not just hear this background murmur, it will have the sensitivity to pick out individual voices from the chorus. It could pinpoint the specific song of a single pair of supermassive black holes winding their way toward a cataclysmic merger in a distant galaxy. This would transform the hum from a statistical curiosity into a rich symphony of identifiable players. By opening this low-frequency window, LISA will give us a completely new sense with which to perceive the cosmos, revealing the hidden lives of the universe's most massive objects. This space-based observatory represents the next great leap, a testament to our species' relentless drive to listen more closely. And while its launch is still years away, the hunt for the hum does not stand still. Another frontier in this great hunt unfolds not with microphones for spacetime, but with cameras pointed at the oldest light in existence. The cosmic microwave background is the faint, cold glow that fills the entire sky, the remnant heat from the Big Bang itself released when the universe was a mere infant. This ancient light is not just a passive relic, it is a canvas, and primordial gravitational waves would have left a specific mark upon it. As those vast ripples from the dawn of time propagated through the searing early universe, they would have gently squeezed and stretched the fabric of space, subtly affecting the direction or polarization of the light traveling through it. This creates a unique, swirling pattern imprinted on the cosmic background radiation, a signature known as B-mode polarization. Finding this pattern is the ultimate goal. It is not like listening for the wave itself, but rather like discovering the fossilized footprint of the wave, left in the mud of the early cosmos. The hunt for this ghostly imprint drives astronomers to the most extreme environments on Earth. High on the Antarctic Plateau at the South Pole, experiments like BICEP and the Keck Array scan the frigid, dry sky. The air here is incredibly thin and holds almost no water vapor, making it one of the clearest windows on Earth for observing the subtle nuances of the cosmic microwave background. They are searching for that specific curl in the polarization, a signal so incredibly faint it is easily drowned out by closer cosmic phenomena, like dust within our own galaxy. This method provides a completely different line of evidence. It probes the universe not by feeling the ripples directly, but by seeing how those ripples affected the very first light. A detection here would be monumental, offering compelling and independent proof that the primordial stochastic background is real. It represents a powerful multi-messenger approach where different methods from pulsar timing to cosmic light all converge on the same profound truth. Yet, as our instruments inch closer to the required sensitivity, they begin to brush against a far more fundamental barrier, a limit woven into the fabric of reality by the rules of quantum mechanics. There is a final, fundamental barrier to silence, one woven into the fabric of reality by the rules of quantum mechanics. As detectors become impossibly sensitive, they eventually bump against the Heisenberg uncertainty principle. This is not a limit of engineering, but of the universe itself. It dictates a fundamental fuzziness at the smallest scales, meaning you can never know the exact position and the exact momentum of a particle at the same time. For our laser beams, this translates to a constant, irreducible quantum noise. The stream of photons that makes up the laser beam does not arrive in a perfectly smooth wave. Instead, the exact number and the precise phase or rhythm of these photons fluctuate randomly. This creates a hiss of uncertainty at the detector, a quantum static that obscures the faintest signals. For decades, this was considered the ultimate, unbreakable limit to precision. But scientists have found a way to cheat this cosmic rule, not by breaking the laws of physics, but by bending them to our will. The solution is a stunning quantum trick known as squeezed light. The core idea is to manipulate the very nature of the laser light's uncertainty. The Heisenberg principle does not say you cannot reduce uncertainty, only that you cannot reduce it in all properties at once. So, physicists use special crystals to squeeze the light, deliberately increasing the fuzziness in one property, say the exact number of photons, in order to achieve a spectacular reduction in the fuzziness of another property, like their precise phase or timing. It is a quantum trade-off, You accept more noise in a dimension you do not care about to gain an unprecedented quiet in the dimension you are trying to measure. This is not a theoretical concept. Advanced LIGO has already implemented squeezed light into its operations, pushing its sensitivity beyond what was once thought to be an absolute wall. It is the equivalent of using quantum mechanics itself to quiet the very tools we use for measurement, turning down the static of reality to hear a whisper more clearly. This innovation is absolutely crucial for the next generation of detectors, the machines that will finally, definitively, hear the universe's oldest song. So, with all this ingenuity, from planet-sized ears to quantum tricks, what would it actually mean if we succeeded? What profound truths would a confirmed detection of the cosmic hum reveal? A confirmed detection of this cosmic hum would instantly redraw our map of the universe. This is not a map of stars and galaxies, but a gravitational census of its most violent inhabitants. By analyzing the hum's strength and character, we could count the invisible. We would learn the true population of black holes and neutron stars across all of cosmic time, understanding how often they form, how they dance, and how they merge in the dark. It would reveal a hidden cosmos, a landscape of massive objects we can only feel, not see. Yet, finding the astrophysical background would be only the beginning. The truly revolutionary discovery would be isolating the primordial component within that hum. That faint whisper from the universe's first instant would be direct, incontrovertible evidence for cosmic inflation. It would be like finding the original blueprint for the entire cosmos, validating a theory that has, until now, rested on compelling but indirect clues. This signal would let us probe energies so extreme they are 1 trillion times more powerful than anything we can create in the Large Hadron Collider. At these energies, the very forces of nature are thought to unify, and the quantum nature of gravity itself might finally become apparent. This is the ultimate frontier, a chance to test theories like string theory or loop quantum gravity, to understand how the force that shapes the cosmos emerges from the fuzzy quantum world. This background hum is far more than just another signal to catalog. It is a new cosmological probe, a fossilized record of the universe's entire history, written not in stone or light, but in the very stretching and squeezing of spacetime. Its implications ripple out from the practical counting of black holes to the most profound questions of existence, connecting the vast dance of galaxies to the quantum jitter of the vacuum. But the journey does not end with a simple detection. The next, even greater challenge is characterization. We must learn to read the subtle nuances in this universal whisper, to decode the specific stories it contains. The sheer volume of data these detectors produce is a universe in itself. Every second of observation from a global network of interferometers and pulsar timing arrays generates a torrent of numbers, a chaotic digital ocean where the signal we seek is a single, faint drop. Traditional statistical methods, while powerful, can struggle to find the most subtle patterns in this noise. This is where a new kind of hunter enters the search: artificial intelligence. Machine learning algorithms are being trained to become expert listeners. They are not given explicit instructions on what to look for, but are instead fed vast amounts of data, both simulated signals and real detector noise. Over time, they learn to recognize the unique fingerprint of a gravitational wave glitch, the subtle tremor of an earthquake, or the random hiss of quantum noise. They become brilliant at classification, sorting the cacophony into its constituent parts. More importantly, these algorithms can search for the stochastic background in entirely novel ways, identifying complex, multi-dimensional correlations across different detectors and different timescales that might be invisible to the human eye. They act as tireless assistants, working day and night to sift through the mountain of data, accelerating the pace of discovery and potentially revealing faint features in the hum that we never thought to look for. This powerful marriage of theoretical physics and cutting-edge computer science is no longer a luxury. It is an absolute necessity for the next phase of the hunt. As our ability to analyze this data improves, we begin to ask a more refined question. Is this cosmic hum the same in every direction, or does it hold hidden patterns? This leads us to the concept of anisotropies. The gravitational wave background might not be a perfectly uniform hiss. Just as a calm ocean has subtle variations in its surface, this space-time hum could be slightly louder in some parts of the sky and quieter in others. These tiny fluctuations, these anisotropies, would be a treasure trove of information. A brighter patch could point toward a local concentration of merging supermassive black holes, or perhaps a nearby cosmic string. Mapping these subtle differences would transform the background from a mere sound into an image, a rough but revolutionary map of the gravitational universe, revealing the hidden structure of violence across the cosmos. This quiet hum holds a secret geography. While we often describe the stochastic background as a uniform hiss, the universe is rarely so simple. It is far more likely to be anisotropic, a scientific term meaning its intensity varies slightly depending on which direction you point your ear. This subtle patchiness arises from a simple cosmic truth. The sources of this background are not sprinkled evenly across the void. The millions of binary black holes and neutron stars that contribute to the roar are clustered, gathered into the vast cosmic webs of galaxies and dark matter that structure our universe. Some regions of space simply have a higher density of these violent objects than others. Imagine listening to a massive, cheering crowd from a great distance. At first, it sounds like a single, steady roar, but as your hearing becomes more acute, you start to pick out patches where the sound is slightly louder, where one section of the crowd is more energetic than the rest. That is the goal with gravitational waves, to move from simply hearing the roar to mapping its loud and soft spots. Detecting these anisotropies is the crucial next step after confirming the hum exists. It transforms a monolithic signal into a detailed picture. A brighter patch on this gravitational sky map could point toward a supercluster of galaxies, a region teeming with an overdensity of merging black holes. It might even reveal a single, exceptionally loud and relatively nearby source, a monstrous binary system whose combined murmur stands out from the crowd. This would not just be a new map, it would be a new kind of map, one drawn not with light, but with the echoes of spacetime itself. It would show us the large-scale structure of the cosmos through the lens of its most violent events, adding a profound new dimension to our understanding. This monumental task, of course, is too vast for any single nation or team to undertake alone. It demands a unified effort across the entire globe. This vast, collaborative effort is a symphony of human intellect, a global network of minds and machines all tuned to the same cosmic frequency. The hunt for these space-time ripples is big science in its purest form, a monumental undertaking that no single nation or institution could ever hope to achieve alone. It demands a level of international cooperation that is truly unprecedented. Look at the LIGO-Virgo-Cagra collaboration or the International Pulsar Timing Array. These are not just projects with a few international partners. They are vast, sprawling ecosystems of discovery, uniting thousands of scientists, engineers, and students from dozens of countries across the globe. This collaboration goes far deeper than simply sharing hardware or splitting costs. It is about creating a collective intelligence. Each group brings its own unique expertise, from the subtle art of suspending mirrors in isolation to the complex statistical models needed to analyze pulsar data. They pool their data streams, their computational power, and most importantly, their perspectives. A potential signal identified by one team is immediately subjected to a global crucible of scrutiny, examined and re-examined from every conceivable angle. This diversity of thought is our strongest defense against error and bias. In a search where the prize is a whisper buried under a mountain of noise, this collective, worldwide effort is not just a good idea. It is the only way the hunt can possibly succeed. The shared goal of listening to the universe's oldest song transcends politics and borders, uniting humanity in a single, profound scientific quest. This spirit of global partnership is pushed to its absolute limit when we focus on the specific, maddening challenges of working with pulsar timing arrays. The pulsars themselves are perfect cosmic clocks, but the path their signals take to reach us is anything but clean. The radio pulses must travel for thousands of years through the messy, turbulent interstellar medium. This vast space is not a perfect vacuum. It is filled with a thin, ionized gas of electrons that acts like a cosmic prism, bending and scattering the radio waves. This creates a phenomenon called dispersion, where different frequencies of the pulse arrive at slightly different times. It is the ultimate static, a smearing of the perfect tick of the pulsar clock. To make matters even more complex, the interstellar medium is not static itself. It churns and swirls, creating a dynamic, ever-shifting fog that changes the amount of dispersion from one year to the next, even from 1 month to the next. Correcting for this requires meticulous, continuous monitoring of each pulsar across a wide range of radio frequencies, building a detailed model of the space between us and them. It is a relentless battle against a blurry, moving lens, all to preserve the pristine timing of a pulse that began its journey when human civilization was in its infancy. Only through the combined, patient work of international teams can we hope to model this noise well enough to see the subtle space-time ripples hiding beneath it. That unblinking patience has now borne its first incredible fruit. After more than 15 years of listening, the great pulsar timing arrays have finally heard something. Multiple international collaborations have announced compelling evidence for that low-frequency rumble, the gravitational wave background. This is not yet a final, definitive discovery, but the signal is strong. It is consistent across different teams, and it matches the telltale pattern expected from a universe filled with overlapping waves. To grasp what this required, think of the pulsar as a flawless clock in a damaged delivery system. The pulse leaves on time, a perfect rhythm born from a spinning stellar corpse. But its journey to Earth is a gauntlet of cosmic interference. The first and most significant hurdle is the interstellar medium. This thin soup of ionized gas that fills the space between stars acts like a turbulent prism. It disperses the radio pulse, slowing down its lower frequencies more than its higher ones. The result is a smeared-out signal, a once sharp tick now blurred across a range of arrival times. Correcting for this demands observing each pulsar at multiple radio frequencies simultaneously, building a dynamic, real-time model of this cosmic fog to sharpen the tick back to its original precision. Then there is the motion of our own planet. The Earth is a moving platform orbiting the Sun at 30 kilometers per second. This constant motion means the distance a radio pulse must travel to reach us is always changing. A pulse arriving in January, when Earth is on one side of the Sun, travels a different distance than the same pulse arriving in July. The timing correction for this alone is thousands of nanoseconds, a massive effect that must be calculated and removed with exquisite accuracy. We must even account for the subtle drift of the pulsar itself through the galaxy. a slow, steady motion that gradually changes its distance from us over years. Any one of these unmodeled effects could perfectly mimic the subtle advance or delay of a passing gravitational wave, creating a false signal that vanishes under closer scrutiny, or worse, hiding a real one in plain sight. The recent triumph is a testament to conquering this entire chain of uncertainty. It represents a global refinement of models, a honing of algorithms, and a sheer accumulation of data points over a decade and a half, slowly squeezing the random noise down until this correlated hum began to emerge. This is the power of precision and persistence, a victory for the long game in science. And this newly heard hum does not exist in isolation. It resonates with our deepest questions about the universe's fundamental forces. This newly detected hum is more than just a cosmic sound. It is a direct bridge to the deepest and most stubborn mystery in all of physics. For decades, scientists have struggled to unite the two great pillars of modern science, the quantum world of the tiny and the gravitational world of the vast. Gravity, as described by Einstein, is the smooth, geometric bending of spacetime. The quantum world is a fuzzy, probabilistic realm of jittering particles. They seem fundamentally incompatible, and every attempt to combine them mathematically has failed. Yet, the very first moments of the universe were a domain where these two worlds were forced to meet. At that incredible energy at the instant of the Big Bang, gravity itself must have been a quantum force, jittering and fluctuating like everything else. Those quantum jitters in gravity are what inflation stretched into the primordial gravitational waves we now hunt. This means the stochastic background is not just a fossil, it is a recording of quantum gravity in action. By studying the precise character of these waves, their spectrum and their statistical patterns, we can perform experiments on quantum gravity itself, something no particle collider on Earth will ever be powerful enough to do. The subtle details of this signal act like a cosmic fingerprint. For instance, some versions of string theory predict a specific, faint chorus of waves from a network of vibrating cosmic strings. Loop quantum gravity, another contender, might leave a different statistical mark on the signal. A clear detection of the primordial background could immediately rule out entire classes of theories, providing our first real experimental data from this unreachable energy frontier. It would be a guiding light for theorists pointing toward a complete theory of everything. This quest transforms the hunt from a search for cosmic events into a direct investigation of the fundamental laws that knit reality together. The technology born from this profound search, however, has a way of echoing back into our daily lives in surprising and practical ways. The same quantum-squeezed light that sharpens our view of the cosmos is now being adapted to create unhackable quantum communication networks. This pattern repeats across the entire technological landscape of the hunt. The relentless pursuit of silence for these detectors has forced engineers to conquer vibration with an almost supernatural precision. The multi-stage pendulum suspensions and active isolation systems that protect LIGO mirrors from the rumble of the Earth are now finding their way into the hearts of semiconductor factories. There, the slightest tremor can ruin a microscopic circuit on a silicon wafer, making the vibration control born from fundamental physics a cornerstone of modern manufacturing. Even the computational tools are finding new life. The same sophisticated algorithms designed to find a faint correlated whisper in the data of two distant detectors are now used by financial analysts to spot subtle market trends and by seismologists to identify the unique signature of different types of earthquakes. This is the hidden engine of pure science. The drive to answer a profound, seemingly abstract question forces us to invent new ways of seeing and measuring. We stretch the limits of laser stability, quantum control, and data processing not for a specific product, but for a deeper truth. And in doing so, we create a toolbox of radical innovations that then spills over into medicine, industry, and security, improving daily life in ways we never could have predicted. This technological echo from the hunt for spacetime ripples reveals a beautiful secret: that the path to understanding the universe is also a path to reshaping our own world. This very reshaping now gives us a powerful new tool to solve one of astronomy's most stubborn puzzles: the true expansion rate of the cosmos. This persistent hum could become the universe's newest measuring tape. Right now, one of the biggest arguments in cosmology revolves around a single number, the Hubble constant. This value describes how fast the universe is expanding today, a fundamental key to predicting its ultimate fate. Yet for years, two different methods have stubbornly refused to agree. One approach, using the cosmic microwave background as an ancient ruler, gives one answer. Another, using exploding stars in the nearby universe as mile markers, gives a slightly different one. The discrepancy is small, but it is persistent, hinting that we might be missing something profound in our understanding of physics. This is where the gravitational wave background offers a brilliant, independent path forward. Think of the astrophysical part of the hum as a chorus of countless binary black holes. The loudness of this chorus, its overall amplitude, depends directly on how far away these merging pairs are on average. That average distance is not a random number, it is woven into the fabric of the universe's expansion history. By carefully modeling the population of these black holes and then precisely measuring the strength of the background they create, cosmologists can work backwards to calculate the Hubble constant. This method is completely detached from the traditional cosmic ladder. It does not rely on the physics of ancient light or the precise brightness of exploding stars. It uses the collective roar of spacetime ripples themselves as a new standard candle. A precise measurement from this gravitational wave background could break the deadlock, pointing toward which of the conflicting values is correct, or perhaps revealing that both are subtly wrong and that new physics is required. This transforms the hum from a fascinating signal into a powerful new tool, a fundamental instrument for gravitational wave cosmology. It turns the static of the cosmos into a precise gauge for measuring reality itself. And whenever we develop a new way to measure the universe, we must always be prepared for the one thing it reliably delivers: the completely unexpected. The universe has a consistent habit of surprising us whenever we learn to see it in a new way. The static we are now straining to hear could easily contain a signal that shatters our current understanding. The unique power of this stochastic hunt is its sheer inclusivity. It captures every ripple from every source, whether we know it exists or not. This makes it a perfect discovery machine for the truly exotic. For instance, woven into the hum could be the vibrations of cosmic strings. These are not strings of matter, but hypothetical, one-dimensional cracks in spacetime itself, relics from the universe's first moments of cooling. Think of them as cosmic faults in reality, incredibly thin but unimaginably dense. If they exist, their vibrations and loops would generate a storm of gravitational waves, leaving a distinctive, sharp signature in the background static that no population of black holes could ever mimic. Or perhaps the surprise will come from the dark sector. The hum could carry the faint tremor of dark matter particles, the universe's invisible majority, annihilating or colliding in ways we have never detected. It might even reveal entirely new forces or particles from beyond our standard model of physics, phenomena that operate at energy scales so high they are completely invisible to our particle colliders. The greatest thrill for any scientist is not confirming a prediction, but finding a piece of data that makes no sense at all. a signal that forces us to throw out the old textbooks and dream entirely new theories. This potential for a revolution hiding in the static is what fuels the passion behind this decades-long search. To find such a subtle whisper, however, requires a commitment not measured in years but in generations. The faint correlations that reveal the hum only emerge after thousands of days of patient, uninterrupted listening, a testament to the profound power of simply paying attention for long enough. This search for the cosmic hum is a marathon run over decades. Unlike a single, explosive black hole merger that screams and then fades, the stochastic background reveals itself only through the slow, patient accumulation of data. Its signal is a statistical ghost, a pattern so faint it only emerges when you average together thousands of days, months, and years of observation. Think of it like trying to hear a single, quiet conversation in a stadium of roaring fans. If you listen for just a second, all you hear is noise. But if you record the crowd for an entire season and then carefully analyze the recording, you might finally isolate that soft, underlying murmur of countless individual voices. This is the essence of the hunt, a battle against noise won not with a louder microphone but with sheer temporal endurance. For pulsar timing arrays, the challenge is even more fundamental. The gravitational waves they seek are not short chirps, but long, rolling swells with periods of years or even decades. To even begin to detect one complete cycle of such a wave, you must collect data for at least that long. A 15-year dataset is not just a long observation. It is the absolute minimum required to sample the lowest notes in the cosmic symphony. This long-term perspective fundamentally shapes the science. It demands a rare kind of institutional patience and sustained funding that must outlive political cycles and economic shifts. It relies on the dedication of scientists who may spend their entire careers nurturing a single experiment, knowing they might not live to see its ultimate conclusion. They are planting a tree whose fruit will be harvested by the next generation. The profound payoff for this patience is a record of unmatched value, a continuous, decades-long diary of the universe's gravitational activity. This dataset becomes a time capsule, capturing the subtle heartbeat of the cosmos across a significant stretch of human history. It teaches a humbling lesson that some of nature's most profound truths are not announced with a bang, but whispered over centuries. To even begin to comprehend the subtle patterns hidden within this vast ocean of data, scientists must translate it into a form our eyes can understand, creating maps and graphs that reveal the hidden geography of the cosmic hum. These statistical whispers must be translated into a language our eyes can understand. The raw data from pulsar timing arrays and interferometers is a torrent of numbers, a chaotic digital ocean. To find meaning in this sea of information, scientists rely on the art of data visualization, creating maps and graphs that reveal the hidden structure of the cosmic hum. One of the most fundamental tools is the power spectrum plot. Think of it as an audio equalizer for the universe. The horizontal axis represents the different frequencies, from the deep bass rumble of supermassive black holes to the higher-pitched chirps of smaller mergers. The vertical axis shows the strength or loudness of the signal at each of those frequencies. A flat line would mean silence, but a rising curve tells us that the cosmos is humming, and the specific shape of that curve acts like a fingerprint, pointing toward the dominant source of the vibrations. For an even deeper view, researchers create all-sky maps. These are not pictures of stars and galaxies, but portraits of gravitational wave intensity. They look strikingly similar to the famous maps of the cosmic microwave background, but instead of showing ancient heat, they depict the subtle variations in the space-time ripple background. A common scheme uses a red-blue color scale, where deep red patches indicate regions of the sky where the hum is slightly louder, and blue areas where it is quieter. These visual tools are far more than just pretty pictures. They are essential analytical instruments. A bright red spot on the map might point toward a known supercluster of galaxies, a region so dense with matter that it naturally contains more merging black holes, their collective murmur amplifying the signal. An unexpected pattern could be the first hint of an exotic source, like a nearby cosmic string loop vibrating in the dark. By comparing these maps against theoretical predictions, scientists can test our understanding of the large-scale structure of the universe in an entirely new way. This process of turning abstract mathematical correlations into an intuitive visual landscape is a crucial act of translation. It bridges the vast gap between raw data and human insight, making the invisible tremors of spacetime something we can literally see and explore. This act of translation does not stop at the laboratory door. The same visualizations that guide researchers also become powerful tools for sharing the wonder of this discovery with the world, inviting everyone to see the universe through this new gravitational lens. This vast scientific quest has reached beyond the laboratory to capture the global imagination, transforming passive observers into active hunters. One of the most powerful tools in this effort is a program called Einstein at Home, which invites anyone with a computer and an internet connection to join the search. When your computer is idle, its screensaver can activate, quietly downloading and processing tiny slices of data from LIGO or from Pulsar timing arrays. Your machine becomes one thread in a colossal digital fabric, scanning for the subtle pattern of a gravitational wave that automated systems might have overlooked. This is citizen science at its most profound, a distributed computing model that turns thousands of personal devices into a single, planet-wide supercomputer. The collective power of these volunteered cycles has already led to real discoveries, including previously unknown pulsars, found by the computers of everyday people. This participation creates a powerful bond, making the public true partners in peeling back the layers of the cosmos. The sheer drama of the hunt itself, a story of listening for ripples in the fabric of reality, provides an irresistible narrative for science communication. The announcement of a new detection is not just a dry scientific paper. It is a global event that speaks to our shared curiosity. It showcases the human drama behind the data, the decades of struggle, the brilliant engineering, and the triumphant moment of discovery. This narrative inspires the next generation of physicists, engineers, and programmers, showing them that the biggest questions are still there for the taking. By openly sharing both the exhilarating successes and the frustrating challenges, the scientific community builds a bridge of trust and wonder. It fosters a deep, public appreciation for why we pursue fundamental questions, reinforcing that this expansion of human knowledge belongs to everyone. This vital partnership between the experts and the eager public is the beating heart of modern big science, ensuring the quest is a shared human journey. That shared journey now looks toward an even more sensitive future, as plans are already underway for the next generation of listeners. The current detectors, as stunningly advanced as they are merely the first prototypes. The future lies with projects like the Cosmic Explorer and the Einstein telescope, designed to be exponentially more powerful. The Cosmic Explorer envisions laser interferometers with arms not 4 kilometers long, but 40 kilometers, creating an instrument 10 times more sensitive than advanced LIGO. The Einstein telescope, a European project, plans to build an underground triangular facility with 10-kilometer arms, shielding it from seismic noise and using revolutionary cryogenic technology to cool its mirrors to a point where atomic jitter is almost silenced. These are not minor upgrades, they are leaps into a new realm of hearing. With this vastly improved sensitivity, the faint hum of the stochastic background will not be a subtle statistical whisper, but a clear, rich sound we can dissect in detail. We will move from simply confirming the hum exists to listening to its individual instruments, distinguishing the roar of astrophysical black holes from the possible primordial whisper of inflation. These future observatories will open a window onto nearly the entire history of gravitational waves in the universe, turning the faintest echoes into a symphony we can finally understand. The hunt for whispers is accelerating with a new wave of detectors already on the drawing board. The current generation of instruments is about to receive a dramatic upgrade known as a plus. This is not a simple tweak, but a complete overhaul of LEGO core systems. It will employ a more advanced form of that quantum squeezed light, pushing the uncertainty of the laser beam into an even tighter corner. The mirrors will receive new, ultra-reflective coatings to capture more precious photons, and the laser itself will become significantly more powerful, flooding the arms with a cleaner, stronger beam of light. Together, these enhancements aim to roughly double the observatory's sensitivity. To understand what that means, think of a listener in a noisy room who suddenly gains the ability to block out every other distracting sound. With this new clarity, the volume of the observable universe effectively increases by a factor of 8, bringing thousands of previously silent cosmic events into audible range. But the ambition does not stop there. Looking decades into the future, scientists are designing a machine of almost mythical scale, the Cosmic Explorer. This would be a ground-based interferometer, but its arms would stretch for 40 kilometers, 10 times the length of LEGO current facilities. Such a colossal instrument would be so profoundly sensitive that it could achieve in mere months what current detectors might take years to even hint at. The stochastic background from countless binary black holes would shift from a subtle statistical murmur to a clear, unmistakable roar. It could potentially hear the individual chirps of the very first stars and black holes in the universe, the pioneers that lit up the cosmic dark ages. These projects represent a continuous evolution, a relentless drive to hear more, to hear deeper. Each new level of sensitivity is like turning up the resolution on a blurry photograph, revealing finer details and fainter objects we never knew were there. The gravitational wave symphony will become richer, with more instruments and more complex melodies coming into focus. This pursuit of greater sensitivity is a journey with no finish line, a fundamental expression of human curiosity. It asks a simple, profound question: what else is out there, and can we become quiet enough to finally hear it? This relentless drive to listen, to map the unseen, springs from something deeply human. Our species has always looked up at the night sky and wondered. We charted the stars, built telescopes to see farther, and now we are crafting instruments to feel the subtle tremors of reality itself. This hunt for echoes from nowhere is the latest chapter in that ancient story, a direct line from Albert Einstein scribbling his equations in Berlin to a global team of thousands fine-tuning a laser in Louisiana or modeling interstellar static in a data center. They are all answering the same primal call, asking the same fundamental questions that have haunted us for millennia. Where did all of this come from? What is the universe truly made of, and what are the rules that govern its grand dance? This is not a passive inquiry. It is a proactive, arduous quest that demands everything we have. It pushes the boundaries of our technology, forcing us to invent new ways to see, or in this case, to hear. It tests our collective ingenuity, solving problems of vibration and quantum noise that seemed insurmountable a generation ago. And above all, it demands a profound patience, the kind that plants trees for future generations to sit under. This journey reminds us that wonder is not confined to what we can see. The cosmos is filled with phenomena that are completely invisible to light, hidden in the dark, silent fabric of spacetime. By learning to feel its vibrations, we are opening a new sense, granting ourselves a deeper, more intimate connection to the cosmos than ever before. These faint ripples are a siren song from the void, a challenge flung at our feet. We could have ignored it, content with the universe we could see. Instead, we chose to accept. We are building the ears to hear its oldest stories, and in that audacious act, we are not just discovering the universe, we are rediscovering our own capacity for awe and expanding the very definition of what is possible. Our journey through this cosmic hunt has been a profound exploration of scale, from the quantum jitter of a single photon to the slow, patient listening across our entire galaxy. We have witnessed how the subtle trembling of spacetime connects the vast dance of black holes to the fundamental rules that knit our reality together. This is not merely a technical achievement, it is a new kind of conversation with the cosmos. The laser interferometers and pulsar timing arrays are more than just machines. They are extensions of our senses, colossal ears built to catch the universe's oldest songs. We have learned to cheat noise with quantum-squeezed light and to find patterns in chaos with brilliant data analysis, all in pursuit of a whisper that has traveled since the beginning of time. The implications of truly hearing this hum are staggering. It would let us take a gravitational census of every black hole collision in history and potentially read the direct telegram from the instant of creation. This entire endeavor stands as a powerful monument to what we can accomplish together. It is fueled by international collaboration, by a dedication that spans generations, and by the simple, relentless human need to ask what lies beyond the known. While the full, definitive symphony of the stochastic background is still coming into focus, the progress is undeniable. We are closer than ever to turning a faint statistical murmur into a clear voice. The universe has been speaking this language of ripples for billions of years. We are only just now, with immense patience and ingenuity, learning how to hear it. We would love to hear your thoughts on this incredible quest in the comments below, and if you want to continue exploring the mysteries of the cosmos with us, please subscribe.